Welcome to this video. So we are going to discuss two topics today. We are going to first start with the idea of angle of contact, in which we basically talk about how a liquid interacts with uh, other states of matter, that is air and solids. And then we'll be moving on, basically how does a liquid behave when it is introduced in narrow tubes or capillaries, which is basically uh, the topic of capillary action. So it's pretty fascinating how liquid behaves in these kinds of situations. So let's begin. So basically, there are two kinds of forces which a liquid has when it is interacting with some kind of matter. When it interacts with itself, we say, let's say this is some kind of a drop of liquid. Let's say it's of this shape only. So the particles inside the liquid, they exert some intermolecular forces on each other. They tend to interact with each other. So when they interact with each other, they attract each other. Okay. So because of which we say that okay, this force, which is basically keeping the molecules close to each other, they are making the bulk of the uh, liquid. Okay, when these forces they become very very strong, the intermolecular distances become very very small. In that case, we can say that the liquid has changed its state of matter. But here, these are the intermolecular forces which we have. Okay, that means this is a liquid phase only. These kinds of forces which we have in this phase are called cohesive forces. So they basically exist in like kind of particles, exist between particles of same kind. Okay. Next we have adhesive forces. So in effect, we are not changing the nature of forces here. We are basically saying that ki how liquid behave with itself and how it interacts with other things or other states of matter. So these adhesive forces, they are basically seen when a liquid is, let's say, put over a top of a glass plate like this. So basically, this is the case of a what we say a mercury drop. You would have seen. In case of a mercury drop, if you have a mercury drop, that mercury drop, when it is placed on a glass plate like this, uh, it basically tends to clump up together. That means that the mercury drop does not spread on the glass plate. So this is a kind of very interesting and curious phenomena. How does the liquid basically, when placed on a glass plate, behave in such a way that it is not actually spreading itself out on the surface. Rather, it's clumping together. So this phenomena is basically possible because these forces where the particles are attracting each other within the mercury drop are stronger. There is one other force called adhesive force. This force is also part of the action. So these particles which are here on this on the drop at the bottom of the liquid, they interact with the glass. Uh, they interact with the glass molecules. So these glass molecules, which are at the bottom of the um, glass plate, they interact with this mercury drop and they try to create a force in downward direction. So this is the downward direction which helps this mercury drop get kept tied down to the glass plate. So this is what is called adhesive force. So they exist between atoms or particles of dissimilar kind, dissimilar nature. They are not of the same nature. So these glass drops, which are attracted towards this glass plate, they are um, basically uh, spread in the surface like this. So we have a simple idea. If the cohesive forces in a liquid are stronger than the adhesive forces, which are basically keeping them tied down to the glass plate, then they form a shape like this. The mercury drop will make a shape like this, or whatever liquid it is. So this is because of the fact that the adhesive forces, they are getting attracted towards the glass plate. So, but this attractive force is not as strong enough in comparison to the internal forces of the liquid drop. Because of the internal forces of liquid drop, they are such strong that they are minimizing the surface of the mercury with the glass drop. They are able to create some surface with the glass plate, but that is because of the weak forces between the glass plate and the mercury. Stronger forces exist in the mercury drop itself, because of which it has no incentive to create these strong forces here. It cannot create any strong forces by making the surface bigger. And this is what happens. And okay, this happened here that the forces are weak. That's why we have no incentive to create a large surface area. In case of a water drop, when it is placed on a glass plate, it forms a surface like this. And from here, we can begin with the idea of angle of contact. So, so we have basically mercury drop, which is like this. This is placed on a plate like this, and this is the angle which it was making. This angle is some theta, and now the angle which the surface makes, like this, this surface which it makes, uh, where this surface is the liquid air interface. So we say that okay, what angle this surface makes with the glass plate. There is one acute angle which I have made here. where is the liquid solid interface, right? This angle was one of the angles, right? There is one more angle. So this is the other angle, other surface basically. This is the liquid solid interface. So basically we need the involvement of the fluid, right? We are studying fluid mechanics. So what is the angle which the liquid solid is making, interface is making, and the liquid air interface is making? The angle between these two lines is called the angle theta. This is called the angle of contact. Next we have this air, or sorry, this water drop. So as this water drop is placed on this glass plate, placed on this glass plate, the angle which again this liquid air liquid air interface makes with the liquid solid interface. This angle is again the angle of contact. So basically reiterating my point, this uh, basically angle which is angle of contact, if we have theta less than 90 degree, then we basically can say that the cohesive forces uh, of the fluid are less than the adhesive forces. That is, the adhesive forces are stronger, which we were saying that the particles at the bottom of the liquid are attracted very well with the particles of the solid. So they are forming stronger bonds with the particle of the solid. So because of stronger bond formation, the energy release is higher. This higher energy release can be used to make this bigger surface. Then if this angle of contact theta is more than 90 degrees, as was in the previous case of the mercury drop, we say the cohesive forces are stronger. That is, the particles are making weaker bonds with the glass plate, so they don't have any incentive to form a bigger surface area. So they form a smaller surface area. This is called adhesive forces. So this is the cases of uh, angle of contact being more than 90 degrees. So next we want to apply this idea uh, into the case of a capillary. What happens when a small capillary is uh, inserted in a liquid surface? So when it is exerted or it is put in a liquid surface, two things can happen. Either the liquid will rise inside the surface or the liquid may fall inside the capillary. So when this capillary is pulled or is put inside this surface, the mercury level will actually go down. So we can simply say this is the cases when angle of contact is less than 90 degree, and this is the cases when angle of contact is more than 90 degree. So this is what we have in the idea of capillary action. So basically these are the two cases which we have. Our objective here is to obtain that to what height or to what depth will this liquid rise or fall inside a capillary. So this is what a capillary is. So let us take the case when the liquid is rising inside a capillary. So we have this force is acting like this, force F, which is acting in upward direction on the capillary. So this is the cross-section view of the capillary. These are how the forces are acting. F and the angle which the force makes with the solid surface of capillary is the same angle which we are talking about, angle of contact. So this angle is theta. So there is some kind of depression which is formed inside the capillary like this. So angle theta, that we know. We will just want to find out what is the force exerted by this surface tension force F on this whole section of the fluid which is rising inside the capillary. So basically, we have some kind of action reaction pair developing here. We know that the fluid inside this capillary will exert a force on the capillary in downward direction, and its reaction is exerted by the capillary on this fluid in this direction so as to pull the fluid in upward direction. So it will pull the fluid up till some height h. Okay. So we can approximate that here to what weight of the fluid will be pulled inside the capillary. Let's say the radius of the capillary is some r. So that is that much we know. We know the surface tension. Let's say S is the surface tension. R is the radius of the capillary. So we have this data. So basically, the surface tension force which would be acting on the periphery of the uh, sub-hemispherical surface which we have drawn would be simply surface tension S into 2 pi r, and we'll have to just take the cos component of it. So S into 2 pi r cos theta. Now this force which is acting in vertical direction, which balance the whole section of the fluid inside the capillary. So its density rho, its volume pi r square h, and its action to gravity g. So this gives us the value of height h to which it will rise. So this cancels out. So this is simply 2s cos theta is equal to rho r h g, and h is equal to 2s cos theta upon rho g r. So this is the height to which the fluid will rise inside a capillary if its radius is r, angle of contact is theta, and surface tension of the fluid is S. Rho is the density of the fluid. So it has pretty fascinating, basically, applications. For example, what would happen if I were to tilt the capillary at some angle theta? Would it rise to a different height, or would it rise to the same height? So it has a pretty straightforward answer. When we basically tilt the capillary, right? Um, we are saying that okay, now the capillary is making some angle theta. So there will be some force acting on the fluid, and some angle of it would basically uh, exert a force on my capillary is liquid to rise in the capillary. And let us take a perspective of uh, pressure difference. Now, if I have this capillary, and in this capillary, I have this uh, same uh, liquid which it has risen to some height h. One question can be, what about the pressure difference between points A and B inside this liquid? Is that applicable here? So the answer is yes, we can apply this here. If we are saying that this sub-hemisphere, right, it has some radius A. So we can easily say that this sub-hemisphere A, it will have the value some r upon cos theta, something like that. Because what was our formula? It was 2s cos theta upon rho g r is equal to h, right? So if you put this cos theta beneath it, this r by cos theta becomes a. So this becomes a very uh, nifty formula. 2s by rho g a is equal to h, where a is the uh, radius of the subhemisphere of the cavity. Cavity means or the meniscus. So this is the meniscus basically, right? This is whole thing is called a meniscus. So its radius is a. So this radius a we can use to actually figure out what is the pressure difference at a depth h. If we use this further, we'll get 2s by A is equal to rho GH, which is the pressure difference between points B and C. So pressure difference between B, I can say PC minus PB is equal to rho GH, right? Then we can say, okay, PC minus PB is rho GH, but we know that PC is nothing but PA. Okay, C is also at the level of atmosphere. C and atmospheric pressure would be same, and A is also in atmosphere. So this means that PA minus PB is equal to rho GH. And this means that PB minus PA is equal to rho GH. That means pressure difference across this kind of meniscus is basically 2S by A, 2S upon A, right? So as you can see here, this pressure difference is basically uh, decided by what is the surface tension and what is the uh, radius of this subhemispherical surface. So the point is that this radius of the subhemispherical surface, this is a constant for a given capillary and given liquid. Okay, the liquid will have the same angle of contact with that capillary if it is tilted. So if we tilt that capillary like this, right? So this is where we began our discussion that what would be the height to which it will rise, which we are basically hypothesizing it will be h only. Let's say it is h dash, and what length of the fluid will go inside this capillary. So we are saying that the radius of the capillary r has remained the same, right? The angle of contact theta, which the forces make with the solid surface of the capillary, are also the same. So that means that the pressure difference across the points, let's say this point is some E, and let's say this point is some F, is also 2S by A. So this 2S by A pressure difference between points E and F is same as in this case only. So that means that even in this case, we will say delta P is 2S by A, right? If I were to calculate it from a new perspective, what will I say? I'll say that the pressure difference between points E and F is 2S by A. So this matches the pressure difference between points A and B here, 2S by A only. So that means the height to which the fluid will rise in this new capillary H dash will be same as that in this case, that is H. So this is what basically pressure difference helps us in finding. Rather than looking in terms of force, how the force is acting uh, and what kind of fluid it is pulling, we'll say that there is some pressure difference. That pressure difference is causing the liquid to rise in this fluid up till this height. And this height should be equal to the height of the fluid in the original case. So if let's say we have tilted the um, capillary by some angle alpha. So we'll say L cos alpha is equal to H dash, right? So this is basically our final result. And H dash is equal to H. So we can find what is L. The L will be H by cos alpha. So I want to basically recreate a logical sequence in this whole derivation. First, what we did is that we basically evaluated what is the value of depth h or height h through which a liquid will go through if it is immersed in a liquid uh, of density rho and surface tension s. If we are given the radius of the capillary, that is r, and the angle of contact. So surface tension and angle of contact, they are the properties of the liquid that we have learned. Okay. And in fact, that is basically what is the point of the whole thing in terms of theoretical point of view. Um, then we said that, okay, what would happen if we tilt the whole system? By system, we mean the capillary. So we said that it would be very basically convenient if we can find some kind of pressure difference because uh, it's because of pressure difference only that matlab, things go up and down inside a fluid. So we evaluated that. We said that, okay, in our first case, like in this case, what is the pressure difference between points A and B, right? So we found that, and we found that that value, uh, that is PA minus PB, which should be equal to rho GH. That rho GH is what we can find using our force derivation. So we said that this value rho GH is simply 2s by A. Okay, so this is the point basically. We said that pressure difference PA minus PP, this is rho GH. And then we said that okay, this rho GH is equal to 2s by A. Okay, that we said by using R upon cos theta is equal to the radius of the uh, subhemispherical meniscus. So we said that this pressure difference is only depending upon the fluid and the radius of that subhemispherical meniscus A. So even in the case when we have tilted the fluid, these two factors are not going to change. S and A are not going to change, because of which this factor, which is it is equal to rho gh, is not going to change. So it was going to rise the same height in this tilted capillary as it rose in the original one. And why did A did not change? A did not change because the radius of the capillary did not change and the angle of contact did not change. So all the properties of the capillary and the liquid remain the same, even if the capillary tilted. So that's why we have come to this conclusion that again H dash is equal to H, but H dash is equal to L cos alpha. So L is equal to H by cos alpha. So that's it for today. Thank you for joining.